this is a lecture about weather and climate extremes. My name is Jana Sillmann. I'm research director at the Center for International Climate Research in Oslo in Norway, and participant of this EXtremeClimTwin project. So in this lecture, I will touch upon what are extreme events, how do we define or calculate extreme events. I give examples of the extreme value statistics and also indices for climate extremes. I talk a little bit about the findings assessed in the last report of the Intergovernmental Panel on Climate Change. And I also talk about the risk framework where climate extremes play an important role. So, what is an extreme event? If you start from the Oxford Dictionary, you find words like extreme is reaching a high or the highest degree, very great, or not usual, exceptional, or very severe or serious. And an event is a thing that happens or takes place, especially one of importance. Okay. So in the climate context, we of course become a little bit more specific, and we define an extreme event as the occurrence of a value of a weather variable above or below a threshold near the upper or lower ends of the range of its observed values in a specific region. That sounds very theoretically, but I illustrated a little bit later. But you just keep in mind it's a value that is far outside of the at the far end of a distribution of a weather variable like temperature or precipitation. And we can also often use return periods or the expression return period, return value to express extreme values, which is an estimate of the average time interval between occurrences of an event, like a flood or extreme rainfall, of a defined size or intensity. Again, this sounds very theoretically, but if you think about a 100-year flood, that is something we have defined because we have a long record of observation of flood levels. And then we can say, okay, this kind of flood level has appeared in 100 years, according to these observations. And then we define it as with a 100-year flood. So on average, this kind of flood level intensity only happens once in 100 years. So that's also how we define the rareness of an extreme. Like a 1,000-year flood is much more intense and much rarer than a 100-year flood, for instance. But the thing about extreme events, even if we narrow it down in the context of weather or climate science, an extreme event is still different and across a very wide range of space and time scale. So a drought is covering a much larger extent of area and is much longer than a heavy rainfall, for instance, in a summer storm. So we have to keep in mind that also time and space plays a role in the definition of extreme events. And then also what you find in the literature when you read about extreme events, there's lots of ways to capture extreme events. And as I said, return values we can use, or exceedance over a threshold. Here, this is one example. For instance, the threshold often picked is the 10th or the 90th percentile of daily temperature or rainfall. And then return period, but also papers use the language of unprecedented events. So they look at the record and look at it, and then they look in the future and say, this has never occurred in the past in our observation, so this is an unprecedented event. And as I said, it can range from very small scale, a hailstorm, to very large scale, like a drought or heat wave. And the other characteristic to keep in mind of extremes, when you look at in a global perspective, if you want to define a heat wave or extreme rainfall, then what is very, very extreme at one location may be normal in another location. For instance, a heat wave that appears hot to us in Norway may be just a pleasant temperature in Southern Europe or in the tropics. So so we have to, it's also relative what we perceive as extreme. So just the example of the weather forecast from Novi that I just yesterday retrieved from the Norwegian weather service called UR. And here you see the weather for today in the between 16, 18 degrees forecasted, and in the coming days it's also going up to 24 degrees. So it is according to the I go to this one. So according to the climatology of your place, Novi Sad, 18 degrees is about the high range of April temperature. So for you, you probably feel this April is quite warm compared to other Aprils that could be, for instance, at the blue curve, as cold as 8 degrees. So year by year, we have temperature variation, and some Aprils could be very, very hot. Some Aprils are cold, and the most of the Aprils are in the middle between 8 and 18 or 20 degrees. And this is kind of projected to the right-hand side. This graph shows the temperature distribution at a specific place, like Novi Sad, for April, for instance. And we have very cold temperatures when in April is 8 degrees, and we have very hot temperatures when in April is 20 degrees or warmer. And most of the Aprils lie in between. So now the extremes are anything that is in the tail of this distribution, very cold or very hot. Yeah. So, but as I said, depending on where you live, 18 degrees could be quite hot, or in the polar zone for an April, or it could be just average. So, and we in the as society, we humans, we have adapted to all these climate zones we find on our globe. For instance, in the polar regions, people have, they live in very, for us, extreme conditions, extreme cold, extreme harsh and snow conditions. We have people living in the forest or tundra and other areas. We have people living in other areas where it's there's no trees, and people even live in the savannah or in the deserts and find their ways where it's really hot. So so extremes is something relative to where you live and what is the relative climatology of the place we are looking at. So this is just to for you to get a feeling of what is when we talk about extreme in the sense of how we perceive it as well. And this is something I took from the workshop day 1. We had a lecture by Manfred Mudelsee, who put out this climate equation. And he said the temperature is composed of, for instance, the trend, the outlier, which he called extreme also, and the noise, the spread of variability. So when I mean, you could see it as the extreme, but when I hear outlier, we also have to be a little bit cautious what we mean by outlier versus extreme can have different meanings. So an extreme is something, as I said, is in the climatology of climate variable in the far out tails. But then outliers could also be when you have a measurement series And all of a sudden, there's a very extreme, very high value. That could be because the measurement device has broken, or they have changed something, or so it's also outliers could also be something that doesn't belong to this time series or to this yeah, measurement side. So that's not what I mean with extreme event. I'm not meaning things that don't belong to this climate distribution or a climate variable distribution. It's not an outlier in the sense that this is a mistake or an error in the measurement or in the time series. It is something extreme, which is outside or in the tails of the distribution. But also, what is an extreme is also that it causes a significant loss of life or property. That's also what we perceive or associate with extreme events. They can cause a tremendous economic losses. And we have seen in the recent years a lot these pictures of tropical cyclones hitting an area and causing a lot of damage, or heat waves where we saw a lot of people died from the heat, or we saw floods in Australia, for instance, and we saw strong wildfires in California in the news. So this is also extreme events. They are significant. They are important to our society because they cause a lot of damage and monetary damage, not only the loss of life. Both is important. And in some cases, it's more loss of life. In some cases, it's property damage. In some cases, it's both. That's why in the context of the Intergovernmental Panel on Climate Change, we have this propeller diagram that says the risk from an extreme event is not only the weather extreme, but also how it affects us. And so the weather extreme events are not just rare in the statistical sense events, but they have a high impact. And that's what makes them important for our society. And the high impact is affected by how vulnerable we are to such a extreme event and how much we are exposed. Are we there when the storm hits, or are we somewhere in a safe place? And also for heat waves, for instance, if we are older, we are more vulnerable to the heat than if we are in our 20s. Okay, so statistically, extreme events are rare events. So societally is events with high impact as well. So I talked a lot about the Intergovernmental Panel on Climate Change. This is an activity or an assessment launched by the World Meteorological Organization and the United Nations Environment Program in 1988 to assess all the literature on climate change and to show what do we know about climate change. And there have been so far 5 reports out there. They come every 6 or 7 years. These pictures show the 5th assessment report cycle, which is usually 4 reports: the physical basis, working group 1, the impact, adaptation, vulnerability, which is working group 2, the climate change mitigation, which is working group 3, and the synthesis report. And we are now in the 6th assessment cycle, and working group 1, where I am a lead author, is just finishing their report. So later this year, we will have a new report from the IPCC coming out with very a lot of new information. And in the context of extreme events, I mean, in this cycles of IPCC assessments, there's also special reports in between. And in this 5th assessment cycle, there was a special report on managing the risk of extreme events and disasters to advance climate change adaptation. And that was the joint work of Working Group 1, the physical basis, and the impacts, the Working Group 2. That was in 2012. And in the phase of the 6th assessment report, there came other special reports, like maybe you have heard about them. There was a special report on 1.5 degree warming. There was a special report on land and a special report on ocean. They have all come out in the recent years. Okay, so it's worth looking at least at the summary for policymakers of these reports, because they give you a lot of information about climate change and also about changes in extreme events. Okay, but so I told you we need to see extreme events in a more holistic picture. It's not just the statistics, it's also how they affect our society. And that's what makes out the risk of these extreme events, as I said, in the risk framing of the IPCC. But now in the remaining of my lecture, I mostly focus on the left-hand side, the physical basis of changes or weather and climate extreme events caused by climate change, and a little bit also natural variability. I talk a bit about that. Okay, so this was in the 5th assessment report. The extreme events were covered in several chapters, in the observations, in the evaluation of climate models. You heard a lecture about climate models by Carly the other day. There's also detection and attribution of climate change, the near-term climate change, the long-term climate change. So extremes were covered in these chapters if you want to read more. And I will present some figures in the next slides. So coming back to the original figure of the distribution, we can think this is maybe a temperature distribution, nice Gaussian distribution, and the extremes are in the tails, hot and cold extremes. And with climate change, so this distribution for a specific location and a specific time period, we can get by looking at time series from observed stations or from climate models. And with climate change, this distribution is moving, is shifting, because global warming causes temperatures to increase. And so if you think this is the mean temperature curve for a specific area, then you see when it's getting warmer, so a shift to the right, then the cold tail becomes less smaller, so there's less cold extreme, and the hot tail becomes much warmer or much bigger. So we have much more hot extremes, and some of also unprecedented, as I said before. They have never occurred in the observations. So this is this record hot weather. This is well illustrated also, and can be documented also in observations, that we see this shift, and we see more and more record hot weather in the recent years. So as I said, extreme events are rare in space and time, but the problem is that it also leads to the fact that there is a lack of observational data. So we don't have extreme every day. So it's more difficult to observe and to analyze extreme events, because we have only like once a year an extreme, or not even like 100-year flood, only of course every 100 years. So if you have on average, so if you have only 50 years, how do you determine the 100-year flood? 50 years of data, then it's difficult to extrapolate beyond. So that's a big issue with the extremes, the lack of data, not only in time, but also in space. For instance, in some areas like Europe, we have long records of observations, which also include, of course, extremes. But for instance, in Africa or other areas of the world, we don't have these long records of data. So it's very hard to make a statistics out of extremes based on observation. And as I said, there's a lack of universally valid definitions. So extremes can be expressed in different ways, as I explained before. And also there is a scale mismatch between the observations and model output. That means model output, as you heard from Carly, we have these grid boxes over like 100 kilometers by 100 kilometers, for instance, even coarser or sometimes a higher resolve. And then a point observation that takes, for instance, a rainfall measurement. And this is a point observation, which when you think about extreme rainfall, that has much higher values than when you average over 100 by 100 square kilometers. So that is also a problem if we try to compare observed data from station with model data. So we have to be aware of that. So what we did in the IPCC in the 5th assessment cycle, or in cycles also before, we have two ways mainly. I mean, there's also other ways, but those two approaches were used to assess the changes in climate extremes in this report. One are indices for climate extremes, such as defined by the expert team on climate change detection indices, ETCCDI, and extreme value analysis. And when I talk about extreme value analysis, that's also a way to calculate return values of periods. Okay, so this is a way to come up with a more general definition of an extreme event. As I said, on the one hand, the indices, and on the other hand, the extreme value distribution. But they're all complementary. So we can also come up with the extreme value distribution based on indices. I can explain later. But first, I concentrate on the extreme value distribution, which is a continuous probability distribution developed within the extreme value theory. It is parametric, so you have parameters to define your distribution, and you can calculate return values. What I mean by that is that I showed this nice Gaussian distribution the whole time, but extreme value, the extreme value statistics is we have the generalized extreme value distribution that can describe the behavior, the statistical behavior of extreme events, and there's also Pareto distribution. But the generalized extreme value distribution consists of is a family of distribution, and we call that Frechet, Weilbuhl, and Gumbel. And the main difference between these distributions is their tail behavior. For instance, you see that Frechet has a heavy tail, so it's much further going out in the tail than the Gumbel or the Weilbuhl that is actually a limited tail. So depending on what variable look at, it is determining what kind of extreme value distribution you have, and that is also captured by the shape parameter. But that's I don't want to go into detail. Just that is for extremes we usually don't take we take a special distribution to fit extremes too, and I explain that now. So if you think about the Gaussian distribution, as I just illustrated, for instance, for temperature, what we can do to look into the tail or to specify the tail, we can have our distribution and we can look at the standard deviation. And we can look, everything that is beyond 1 or 2 or 3 standard deviation is our extreme. So we determine the threshold of our tail, for instance, the standard 3 times the standard deviation is our tail, and then we have this tail. But this tail will not capture the full distribution of the extreme event. So we actually, when we are talking about extreme events, we're only interested in the tail. So that's why we're using the generalized extreme value distribution, because that's a distribution that describes only the behavior of the tail, like if it goes very far out or if it ends. So, so to capture only the tail of the distribution, what we do is we use a block maxima approach. So we collect in a distribution, in a time series, for instance, of temperature, we cut it in blocks, like annual blocks. We have 1 year, the next year, and we pick the most extreme out of this block. So this is called block maxima extreme. So if we have 20 years, we have 20 values to fit our distribution to. And there's another approach, peaks of a threshold. There we could take a threshold and say over the 90th percentile, we use the values that are there. That could be 2 or 3. So we have a little bit more data. But you already realize if I only look in detail, my 20 years time series, which I have maybe daily, is reduced to only 20 values to which I have to fit a distribution to. So that's data limitation. So this is shown here. I have this time series with a lot of values every day, but I only pick with the block maxima approach, the top one. So I pick my most extreme value. Or the peaks of threshold is I have this line here, and I depending on how high I put the threshold, I can select 3 values or a lot of values, but then it's not extreme. I mean, I don't capture the extreme. So the picking the right threshold is also crucial here. Okay, and then I can fit to this only those red values. Basically, I can fit my extreme value distribution to, and then I get the behavior of the extreme values in my time series, and I see on the characteristic of the shape parameter what kind of tail behavior my data has. And ideally, I have lots of data, so I don't have only 20 points, but 50 points to get a good estimate of the parameters. And then from this distribution, I can then extrapolate beyond what I have, because I have now a distribution, and then I can calculate my return periods. For instance, if I only have 20 years, but I have the distribution, I can also extrapolate and say, okay, I can calculate a 30-year flood or a 30-year hot event. That's the beauty of having a distribution, because I can extrapolate in the tail. But here also caution, because if you only have 20 years, 20 values, you should not trust the estimate you get for the 1,000-year return period, because that is way beyond what your data can actually tell you. Okay, so that's what that's what we can do. We have this return period, return level plot, and we can see for the 1 or 10 or 100-year return value, we get our curve and the estimate, and the dots are the observations again, and the blue are the uncertainty. And you see, the farther out you go in the tail, the more uncertain the behavior or the estimate of the return period becomes. So with the 20-year data series, you should actually only trust very much the 20-year or return value, but of course you can go a little bit beyond to take the advantages of having a distribution. The problem, or then another issue with this, is also if you have a particular heat event, you need to again think about how you define it. If you have, and this is a problem often occurring when you attribute in the extreme value statistic or in the attribution of extreme values. This paper shows that if you look at only one day, or you look at only one grid point, one place, or you average over a longer time or longer period, that your return values or the distributions are different. They look different. So you get the different values depending on how you define your event. So there you have to be a little bit careful. But in general, if you don't think to represent one particular event, this distribution of extreme values is quite useful. So coming back to the problem with data, as I said, observed records of daily data are limited. If you look at this global historical climatology network map, you see all these red dots are stations, and yeah, some areas are very red and some areas are just blank, meaning there is not much observational data. So it's hard to fit a distribution to make a extreme value distribution in these places where you don't have any observations. And also, what I talked so far is a stationary assumption. So the climate change is the same over the time. So when you have your 20 or 50 years time, it's always, I mean, you assume there's no trend. But the further we come to the present, like the last 10 years, we already have a temperature trend, and in many places, and it becomes even stronger, this trend in the future with more global warming. So we cannot assume stationarity anymore. So we need to include a little bit more information in the distribution. And then, as I said, this all determines the data quality, and stationarity versus non-stationarity. It really determines the quality or the calculation of your return values and the associated uncertainties. So I'm not going into this. So what to say? So the do's, when you think about, I want to apply extreme value statistics because I like statistics and I like this is the way forward to look at extremes, then what you should do is ask why you would fit an extreme value distribution in the first place. Are there other ways to look at extremes? Do you have enough data long enough to draw conclusions from return values you're interested, 20-year, 100-year return values? And consider that your data is non-stationary. So you would need to make a test. If your record has a trend, then you cannot fit a stationary extreme value distribution to it. And don't make it too complicated. Don't overstretch it in terms of what you want to do with, if you only have limited data, or if you want to include more than a trend, but maybe other, we call it covariates, then this has to be supported by how much data you have. And don't go too far out in detail if you only have short data sets, because then your estimates become unreliable. A good book to start with, I really enjoyed this book, is in an introduction to statistical modeling of extreme values, with lots of examples, step by step. He walks you through extreme value statistics, and yeah, there you can learn a lot. Okay, but that's enough for the statistics. Now we come to the indices for climate extreme events, which is more a non-parametric approach. I'm not fitting anything. It's a metrics for absolute count or threshold exceedances of a variable, especially for temperature and precipitation. We are using, for instance, when you think about an index number of frost days. So that is the time series of daily maximum temperatures, and when they go below 0 degrees, then you have a frost day. So you have your annual time series for Novi Sad maybe, and you look how many days in the year are below 0. And then this is your index. And then, like, for instance, we have 30 days frost days in Novi Sad, and we have maybe 100 frost days in Oslo per year. And or heat wave indicators or drought indicators. So here, heat wave indicators often use a threshold of 90%. So if the maximum temperature distribution goes, if the maximum value goes beyond the 90th percentile of the temperature distribution at a specific place, then it's a heat wave, and even So often there is a length parameter also saying it needs to last 3 days. So there could be easy indicators like the frost days, or there could be more complicated indicators like the heat wave indicator. Yeah, so, and as I mentioned previously, the expert team on climate change detection indices, they have been put together by the WMO and CLIVA and another organization to come up with a set of indices that are globally valid and that can be used to monitor extreme events. So what they came up with a set of 27 temperature or precipitation based indicators. And what they did is they hosted workshops across the world in data sparse areas, for instance, Africa, to collect, to basically let the people there use their data if there's available and calculate the indices and give it out to them. So then we have a much larger database of indices than we have for station observation. But because often in countries, the countries don't release their original time series data, but they were fine to release the indices. So with this way, we could cover much more of the globe in terms of characteristics of climate extremes that we would have been with only station observation data net. And these indices for climate extremes have been used in the previous IPCC reports, the fourth assessment report with the previous model generation, CMIP3, the special report on climate extremes, and then this last report, IPCC fifth assessment report with newer model, CMIP5, and the coming report is then based on CMIP6, the global model ensemble. So these indices are widely used, and this is just a table with some of those indices and definitions. You can find it in the IPCC report or in the papers that I uploaded. And all these indices are based on daily temperature, daily minimum and daily maximum temperature, and precipitation data. And here you see frost days, tropical nights, or for instance, the wettest consecutive 5 days is taking from a year, those days in a row that have the most precipitation and is often used as a flood indicator. Or consecutive dry days, and in the bottom is counting how many days in a row are below 1 millimeter precipitation. And that's also often used as a drought indicator, meteorological drought. Okay, and we also had a big effort, as I said, to collecting these observed indices across the world and analyze the trends, the observed trends. This is to be found on this website. You can check, you can even plot your own time series and at a location or for global averages. And there's lots of information about the indices from the observations on this website. And here, just a picture from the last IPCC report where we looked at cold days and warm days. These days where the temperature, the minimum or maximum temperature are below the 10th percentile, or warm days above the 90th percentile. And you see the warm days generally since the 1980s are increasing globally, and the cold days are decreasing globally since the 1980s. And you see the difference here. We have a good coverage with temperature indicators. Only Africa and Amazonian area is gray. But for precipitation, even with this index approach, we have very many gray areas where we don't have long enough data series of the indices to calculate trends. But we can see that an overall wettening of the extreme precipitation in northern latitudes, but and also a reduction in dry days in some areas, and in some areas increasing. But generally, the last report concludes that there is a reduction in cold days and nights, increase in heavy precipitation events, increase in droughts in the Mediterranean and Africa. There's more hot days and nights, and warm spells and heat waves, and droughts in the region of Central North America and Northwest Australia are decreasing. So now, one exercise in the last IPCC report was to see if climate models can represent the extreme events. And so we went from the observations in the ClimIndex database, as I just showed you the website, and the reanalysis, as you heard from Carly, what this is, and the global climate models, the large ensembles, the fifth generation. And we calculated all these indices from all these databases and compared them. And then here, this colorful carpet basically shows you a model evaluation. On the bottom, you see all these models that we took into account. On the left-hand side, you see the indices like consecutive dry days, CDD, or RX 5-day. And then blue means that this particular model, for instance, for RX 5-day, is good compared to all the other models and the reanalysis, and red means it's very bad. And you can see for what depending on what reanalysis you use, the model can be bad or good. So the conclusion was that you actually need good observational databases. The reanalysis for extremes are as same as another model. Because the model influence in the reanalysis basically dominates to what is assimilated in the reanalysis. So you cannot really trust when you look at extremes in reanalysis, don't take it as observations. That's my takeaway. So be careful when you look at reanalysis. It's not observed, and especially for extreme events, you need to be cautious what type of reanalysis data that you use for your analysis. And then we looked at the how the models perform compared to reanalysis, and they're doing a pretty good job showing this trend, which we see also in observation. The cold nights are decreasing, the cold days are decreasing, the warm nights are increasing, so the shading are the models, basically the red and the blue, and the gray, the black one is the observations, and the greens are the reanalysis. What we have found in the last report that that is a good agreement with the observations, but there's of course underestimation of the extreme precipitation. Also, because there's issue, as I said before, with the scaling, the models average over grid box, and there's point estimates in the observation, which is kind of compensated by the indices, but it's not completely with the precipitation indicators. So extreme precipitation is often presented in the models compared to observation. But okay, so saying from this fifth assessment report, conclusions of the model evaluation, we were like, okay, yes, we have confidence in the models to represent the extreme events, at least on the scale of the indices, which are aggregated measures, and we can look into climate change. So we look into the future. What happens to our extremes if the climate warms further? So we looked at different emission scenarios, one that stays below 2 degrees, the blue one, and the one that is worst case, where temperatures reach at the end of the century up to 5 or 8 degrees globally. And this is basically the indication of how far we're shifting this temperature distribution to the right, and how and changing with that details. But it also in the projections, that's also what Carly said. There's not only the uncertainty on what emission pathway we are going. Are we increasing more greenhouse gases? Are we staying below 2 degrees with strong mitigation efforts? Also, what is important to consider within the change is the internal variability and the spread between models. So internal variability means how well, for instance, modes of climate variability are displayed, and the model spread is the difference between individual models. Some models are colder, some models are warmer, and the range of model estimates gives us the estimate of future projection of extreme events. So just to keep that in mind, and the closer in the near term, the internal variability, like how we present circulation patterns and modes of variability, is much more dominant than in the future. Our pathway, what scenario we choose, what future we choose, is dominating. And also for extreme events, as I said, natural variability is an important driver. So for an extreme event to occur, there needs to be the right conditions. And so we have, of course, the long-term climate trend that shows us, okay, the climate becomes warmer, there's more heat waves, and also more intense precipitation events. But for this heat wave to occur, there needs to be good conditions. So for instance, dry surface for a heat wave, it's good to accelerate that it becomes, or that it stays, that the heat accumulates. And also in another good condition is that there is for instance, atmospheric blocking, condition that leads to a lot of incoming sun, no precipitation, no clouds. And if you have this kind of atmospheric condition, then, and combined with the dry soil, then yes, a heat wave can build up. And how long it is sustained, it depends also on the feedbacks with the land and atmosphere, how long this circulation system stays there. And this is for each extreme event, it needs good conditions to happen. And if we understand these conditions better, then we can also draw a conclusion in terms of how to better predict them. That's very important. Yeah, I jump over that. And so for the future, we see a similar trend that we have observed in the recent decades. We see that the coldest minimum temperature, the coldest days, they become warmer. And especially now I'm focusing on the regional patterns here. If you focus on the upper plot, this is based on minimum temperatures, and basically the coldest minimum temperature captured here in a year becomes warmer over time. And especially in the northern latitudes, because there the sea ice melts and the permafrost melts, and so this accelerates the warming of the cold conditions. So the warm conditions, like the daily maximum temperature, so that's the warmest day of the year, they become also hotter, but not as hot as the trend is not as steep as for the cold extremes becoming warmer. But we see also the pattern that is more in the continents, more continental, the heat extremes becoming more extreme in the continents. Okay, and we can see similar patterns when we use extreme value statistics. So here in the same report, we have fitted extreme value statistics to basically the hottest day of the year and the coldest day of the year, here called TXX and TNN. We just saw that in these two plots, which are the indices. so one day, the hottest and the coldest day in the year, we can fit extreme value statistic to it, and then we can extrapolate the 20-year or calculate the 20-year return value. And then you see these plots for the different scenarios. In the upper plots, you see the low emission scenario, so we are staying below 2 degrees. In the lower plot, you see a strong increase in the warming because we have the worst case scenarios with no mitigation of current emissions. And here you see the same pattern. On the right-hand side, it's more the continents that warm, and on the left-hand side for the minimum temperatures is more the northern latitudes that warm a lot. Okay, but this is very general, and this is very hard for people to understand. When you think about these maps, it's very abstract. People, when they experience heat, they often think about heat waves. That's why it's important to look at more indicators that capture these kind of events that we are familiar with from our experience. And so we developed this heat wave magnitude index, and we looked if it can capture observed events, like for instance the heat wave in 2003 that killed a lot of people in France. We can capture, or the heat wave in Russia that caused a lot of problems with air pollution, forest fires, and also crop losses. And mortality, of course, people suffered from the heat. So we can capture these events with one indicator, and I'm not going into detail how to calculate it. But what we can see globally, we looked at the trends of this indicator. So we have the 2010 heat wave, the 2003, and we have also in 1980 the heat wave in the US. And we can look into the future projections and see how such an event, for instance, the Russian 2010 heat wave, was an extremely extreme event at the time. If you see the observations and reanalysis here, the purple and red dots, the 2010 sticks out. But when you go into the future, and especially with the high emission scenario, you see that such extreme events like in Russia 2010 become more frequent. So they become more often and even much hotter and more intense than what we have observed in the present climate. So we are entering unprecedented territory. So, and the same with the European heat wave that wasn't so hot, so we will have more of those events even closer, even in to current climate here in 2030, the first ones appearing. And we looked at this also in a much more regional scale. We looked at the regional and near-term changes in these heat waves captured by the heat wave magnitude index. And here you see projections for the near term from 2000, especially we are in the middle. It's from 2011 to 2040. And we looked every panel, it represents a different regional climate model. So we have different regional climate models combined with different global models. And we captured the hottest heat wave, the strongest heat wave in those 30 years we're looking at for this particular model setup. And you see that when you look at the different models over the same time period, that a heat wave, as in the magnitude of the Russian heat wave, can appear everywhere in Europe at any time in the next 30 years. And that is, of course, overlaid by the or masked or amplified by internal variability, depending when are the conditions right to basically create such a mega heat wave, like in 2010. And you also see that in your area, there's at least 2 or 3 models that simulate such an extreme heat wave in the near term. Okay, I have to look up at the time. So we are now 1 hour. Okay, good. I have time. Okay, so this is now the heat waves. Now I'm going to the extreme precipitation. And as said, we have observed a generally wettening trend In many areas, we see an increase in the extreme precipitation events happening. And we also see that in the future projections. So here I'm using this wettest consecutive 5 days indicator. And the gray is the observations, no, the historical simulations in the past, basically, and in the red is the high emission scenario, the blue is the one where we stay below 2 degrees, and we see that we have an increase globally of these wettest consecutive 5 days by 20% in the future. And that translates in the global map. You see that these strongest increases in this worst case scenario are to be observed in the almost everywhere in the globe. There are some regions that have a stronger increase or affected very much by these by the extremes, and some areas like the Mediterranean or the tip of Africa, there is these are more prone to drying, and not such a strong increase in the wet extremes. But so that is matched with the map on the consecutive dry days, so our meteorological drought indicator, where you see again the Mediterranean in the future will see a strong increase in drought conditions. It becomes drier in this area, also in Australia, in Southern Africa, and in parts of Middle Central America and South America. So these areas are also, we have seen strong wildfires in the recent years. So these are conditions that are favoring also wildfires, which increase in the future then as well. Okay, so these are the general overall patterns of extreme precipitation, but this is again very hard for us. What does it mean for a specific location? It's especially for extreme precipitation, it's so localized that such global maps can only give us an indication in what direction we are heading, but it's difficult to make any planning or to any decision on how to adapt to more precipitation or less precipitation. So that's why we need to go regional. So we have to basically go from global climate models to regional climate models, which cover which are higher resolved than the global models. For instance, I mean, today it's a bit difficult. Today, some of the global models that exist have actually already a higher resolution than the regional models, but the average in the coordinated regional downscaling experiments codex where the models have a grid box size by 50 kilometers, or over Europe 11 kilometers, but it's coarser than the reality when you think about clouds. And a hailstorm 11 kilometers is still quite big, but that's our models becoming more and more fine resolution with the increasing in computing power. And as I said, even global models have now can reach a higher resolution. But this is important to capture extreme events such as convective storms compared to these large-scale systems where an indicator like the 5-day precipitation, maximum precipitation is maybe a good descriptor, but for these convective storms, we really need these high resolved models, like for instance, the weather models. They are very high resolved, or they're also informed by radar information, where we can, for a specific location, we can really see where the rainfall hits. And that's what we try to do also with these kilometer scale high resolved convection resolving models that do not parameterize convective rain, like in the global models or in the coarser regional models. These are models that really resolve these clouds that produce the convection process that produces the heavy rainfall at a 3 or 1 kilometer scale, and you see very much the difference between the resolution. And as I said, this is also today possible with global models, and I don't want to. You can click on this maybe later when you get the presentation, but here in this movie, you see how the tropical cyclones move around the world. So you really have a high resolution model around the world to look at tropical cyclones and to look at extreme precipitation. But this comes at a very, very extreme high computational cost. So for those global models, you usually only have a few years to simulate. So you cannot really simulate hundreds of years as we did with the global models to project future rainfall. So there's a trade-off between how much space, spatial and temporal you can cover, and how fine your resolution should be. So the challenge, as I said, to high-resolution climate simulations is the data availability on local and sub-daily scale. So it's difficult to evaluate these convection permitting high-resolved models because also the observations, sub-daily observations are scarce. Or they're only at specific locations, for instance, in the city, but then we don't have it in the mountains. So, and the higher resolution comes with higher computational expenses. And also we need to find new metrics and indices for extreme events in order to capture or describe and these high resolution extreme events, like small scale events, sub-daily events. How do we compare between regions? So these are questions that the research community is currently dealing with. And one thing I also want to point out is when you go to higher resolution, or also in time or in space, especially with precipitation, you need to keep in mind that what you see in an average over a larger area or over the whole year might not represent what is happening on smaller time scales, for instance, in a season, or for instance, in sub-daily time scale. Here I'm giving the example from a recent paper from a colleague at Cicero who looked at mean precipitation in the summer. Here you see the tip of Norway, southern Norway. And then he looked at the maximum precipitation falling in 1 day, in 1 hour, and in 10 minutes. And what you can see here is that in general, the mean precipitation trend for this area looks, it's becoming drier in southern Norway. But if you go further and further, finer resolved in time, you see that actually it becomes wetter. So there's an increase in the short-term extreme rainfall, like these convective storm, like the summer storm we experienced, that is just at a particular location for an hour, it rains a lot, and that causes a lot of flooding, for instance, in cities. We have observed that in the recent years as well. And so we need to, this high resolution simulations of precipitation is very important to understand the rainfall behavior and not be misled by more the coarser aggregated estimates. And in this study, you also find this analysis to Albania, and I tried to find Serbia here, and I think it's the southern end of Serbia that you can see. And you also, it's not, I think Novi Sad is a little bit further north, but at least you can see that also here the tendency is more a drying. Some areas, small areas become wet, but then if you go to higher time result, like to shorter time scale, 10 minutes, a lot of areas, or especially those that are here, becomes wetter. So these short-term extreme rainfall events become stronger, more intense in the high emission scenario. And another thing to consider when you look at extreme rainfall is the changes. Is not, I mean, we look at the overall change, but for adaptation or for preparing for extreme rainfall, both is important, the frequency and the intensity. So how often such an extreme value, extreme rainfall occurs and how intense it is. So we need to decompose a little bit the precipitation distribution and look at the different components. And what we can see is that both the frequency and the intensity are increasing in the observations that you see in the A and B panel of the right-hand plot, and the CMIP5 models, because they are, of course, coarser than the EOPS station observations, which are gridded as well, but they're still coming from a gridded, from a station observation network. So the models underestimate this increase in frequency and intensity compared to the observations. And that I told you already before, when it's also a general feature coming out of the model evaluation. But both frequency and intensity of extreme events, extreme precipitation, are changing. And that is especially important when you think about adapting to more rainfall. So in the last 5 minutes, I leave some time for questions. I want to also come back to this extremes in the IPCC risk framing, because I think when we analyze extreme events, we also have to keep in mind for what are they important, why are they important to us. And I come back to this figure, and you see that what I explained before, it's the risk from an extreme event is the combination between the hazard, basically the physical part, and the vulnerability and exposure. But in order to make it relevant for society, we need to combine these information. We need to see the extreme weather and climate events in conjunction with the societal development and impacts. And so, as I said, this is done, the right-hand part is done by the working group 2 that deals with impact and adaptation and vulnerability. And a joint report was this ESRs report in 2012. And what this work of this group, I'm showing briefly here, is they try to give information about future risks, and they divide it in, or they describe it as key reasons for concerns due to climate change. And what you see here, this I had shown before, this is the temperature increase depending on the emission scenario. And on the right-hand side, you have these key reasons for concerns. One is extreme weather events. And if you look, even at if we stay below 2 degrees with a low emission scenario, we are still, for extreme events, at the level of moderate to high risk coming from extreme events. That means even now we already are affected and perceive the risk of extreme climate events. And I can give a full lecture on the damages they have caused and how we need to prepare now also for these extremes that we have already basically caused due to the climate warming we have already initiated through our increased emissions. So we already at 1.2 2 degrees around global warming, and we feel the risk of extreme events, and we need to adapt. And that is very important to understand. We're already in the game. We need already now to consider climate change and the risk of extreme events. And especially this special report for global warming of 1.5 degree, which looked into what are the impacts if the warming reaches 1.5 degrees or 2 degrees. What are the differences, for instance, if we go beyond 1.5 degrees, if we reach 2 degrees? And here they disaggregated the climate extremes more also in the impacts to sectors like fluvial flooding, crop yields, heat-related mobility and mortality, tourism, coastal flooding. And you see, we are right now around 1 degree warming, and between 1.5 and 2 degrees, a lot of these sectors see a shift from moderate to high risk. So it really, this report highlights that it matters, especially for extreme events. This half degree between 1.5 and 2 degrees matters if we are in a moderate or high risk from extreme events. In the new IPCC report that is coming up, we have just to give you a teaser, we have extreme events are differently addressed, also to be more accommodating for this common risk framework that I just introduced. We don't scatter extreme events anymore throughout the whole report. There is a full chapter on weather and climate extremes in a changing climate, chapter 11, and the chapter 12, which I was writing with my colleagues. This chapter is about climate change information for regional impact and for risk assessment. So here we in this chapter we try to make a handshake, a link to working group 2 to provide a better assessment or better information for their assessment of risk. And how we did that and how we succeeded, you can then see when the report comes out later this year. Yeah, and if you're interested in more of those more societal related or impact and risk assessment for climate extremes, I can recommend to read this book, which has across basically a journey through the different topics I addressed. It goes from the physical science of climate change and extreme events to case studies for different sectors where climate extremes were analyzed in terms of their impacts and different methods how to analyze impacts, and then also on the socioeconomic consequences of changes in extremes, for instance, for security and conflict, and then also for how our societal transformation can shape extremes and their impact. So this is recommendable, and also here are some papers from which I took information in this lecture if you want to follow up. So with that, I think I'm done. I'm closing this lecture, and I leave 15 minutes for discussion or questions or follow-up clarifications. Thank you very much.